Hello, today I will be giving a talk about what is model theory. So this talk was originally given at the Hudson River Undergraduate Mathematics Conference in spring 2021, I'm recording a version of this talk for YouTube so that you can watch it in perpetuity. Model theory is the study of logical languages, and the best thing to compare this to is programming languages, right? So there's two key properties of programming languages that allow us to analyze them mathematically. The first is that programming languages are bounded, right? You can determine formally whether or not a program is in the programming language or not, right? There's a precise definition of what it means for something to be a correct program in this programming language. And then the other thing is that everything has a precise meaning. So when we have a piece of code, that piece of code has a very precise meaning, at least it should have a very precise meaning in terms of what happens when you execute that code. And in mathematics, everything has a precise meaning. So if beyond that, we also look at a very limited, we limit the language that we use, we can do the same sorts of mathematical analyses. We can look at these very limited, very precise formal languages, and we can ask questions like, what are all of the things that we can say? And how easy is it to say those things? Just like people who analyze computer programming languages can ask, what are the things that you can do with this particular computer programming language? And how easy is it to do those things? So let's take a look at a very specific logical language. This is what's called the first order logic for graphs. And here I'm talking about graphs that don't have any self loops or multi-edges or directed edges, nothing like that. We just care if two vertices are connected to each other or not. So in this logic, we have variables, and the variables have to represent vertices of the graph. They're not allowed to represent anything else. They have to represent vertices of the graph. We have some sort of notation. Here I'm using x tilde y to indicate that x is connected to y by an edge. We have equality to represent if two variables represent the same vertex of the graph. We have quantifiers, so we can say something like for all vertices of a graph, or there exists a vertex of the graph. And we have Boolean logic, and or not, true and false, those sorts of things. And this is it. These five things define this particular language. And that's it. You can't say anything else in this language. If you say something else, it's in an extended version of this language. It's in a different language. You have to study it with different tools. But this here is the first order logic for graphs. And because everything has a precise meaning, and there's this, it's well defined, right? This is all we can do. We can start to ask some questions about, what sorts of things can we say with this language? So let me give you an example. We could say something like, there exists a vertex x such that for all y, it's not the case that x is connected to y. In other words, there's a vertex x which is not connected to every other vertex. In other words, there's an isolated vertex. So we can take these notions that we're familiar with from graph theory, and we can write them in this very formal language. And so we can ask questions about various concepts that show up in graph theory. We can ask, is there a formula that captures this concept? For instance, we might ask, is there a formula that can describe what it means for a graph to be connected? And of course, if we're going to use the language casually, then yeah, we can say that there's a path, but in order to do so, at least in the casual sense that I've shown here, we need ellipses, we need quantifiers over numbers. this looks like first order logic, but it is not first order logic. We've kind of gone beyond first order logic in this particular formula here, which expresses there being a path of connected vertices from one vertex to another. You can use that to describe what it means to be connected. But it turns out, if we're being precise and formal about this, if we're restricting ourselves exclusively to this, to just the 5 things that I showed you, to just, just first order logic of graphs, then we can't talk about whether a graph is connected or not. There's no formula in this language that is true of all of the connected graphs and is false of all of the disconnected graphs. And that's that might seem quite surprising, not as a fact in and of itself, but the fact that we were able to prove it, right? How would you, like, if there is a formula, I can just show you the formula, and maybe it's a complicated formula, and so I have to kind of explain to you why this formula does what it does. But how could we prove that there's no formula that expresses the notion of a graph being connected? Where would we even start? Because there's all of these pieces that work together. There's the Boolean logic, there's the graph theory parts, there's the quantifiers, and they all fit together to make these really complicated formulas. How could we prove that there's no formula that can describe when a graph is connected or not? We can also ask other questions, more ambitious questions than that even. For instance, one of the things that we can say is that, as I've written here, there is a vertex x and there's a vertex y such that x is connected to y, and for any vertex z, if z is connected to x, then z is actually equal to y. In other words, if you unpack that, it takes a little practice to be able to unpack these first order logical formulas. If we unpack that, it reads as there's a vertex x that has exactly one neighbor y. In other words, there's a vertex with degree 1. And so one of the questions that we can ask and we can answer, and I will answer today, is there a simpler way of writing this formula? Now, of course, what does it mean simpler? There's lots of notions of how complex a formula is. You could talk about how many characters it has. But I want to use the notion of how many variables it has, just because that doesn't depend on our particular notation. It turns out that the mathematics about reasoning about the number of variables, and okay, I'm lying a little bit. What I'm actually talking about is the number of quantifiers that are active at any one time. But that's essentially the same as the number of variables in the formula. And so we can say this, and when we have written down this formula here for describing that there's a vertex of degree 1, we notice that it has 3 variables in it, right? It has x, y, and z. And one of the questions we could ask is there a way of writing this down? Is there a way of expressing that there's a vertex of degree 1 using just 2 variables, right? Is that possible? And again, like, how would we even start approaching this problem? Because there's lots of formulas that have 2 variables. Should we just write all of them down? Well, it turns out that there is a tool that allows us to ask and answer these questions in a very intuitive way, and that's called an Ehrenfeucht-Fraïssé game. So here I am over at trkern.github.io/efg. You can find this link. Everything's at trkern.github.io/HRUMC. So you can find that all there. So here's the Ehrenfeucht-Fraïssé game on 2 graphs. The idea here is we have 2 graphs, and we have 2 players. We have spoiler and we have duplicator. Spoiler is player 1. They'll go first and they'll pick a vertex of either graph. And they can pick a vertex in either graph. So they can pick any of these 6 vertices or any of these 4 vertices, whichever ones they want. So let's say that spoiler plays here. And we'll note this, we'll color this vertex in, we'll give it a number, just to indicate that that's the vertex that spoiler picked on turn 1. And duplicator, on their turn, will match this vertex up with a vertex of the other graph. So let's say that duplicator plays here. And so we'll write the same number and color it the same to indicate that these two are the same, these 2 vertices are matched up with one another. And let's say that spoiler now goes here, and we'll label it vertex number 2. Duplicator, on their turn, has to pick a vertex. So on the right graph, vertex 1 and vertex 2 are connected to each other. And so duplicator has to match up vertex 2 so that vertex 1 and vertex 2 are also connected to each other on the left graph. So if the vertices are connected on the right graph, then they have to be connected on the left graph. And if they're not connected, then they have to be matched with vertices that are not connected. So for instance, duplicator can't go in this top left vertex because then vertex 1 and vertex 2 wouldn't be connected here, but they would be connected here. If you know what this means, spoiler and duplicator are cooperatively constructing a partial isomorphism between the 2 graphs, or an isomorphism between subgraphs. So let's say the duplicator plays here. And again, this is a perfectly fine move. Vertices 1 and 2 are connected on the right graph, and vertices 1 and 2 are connected on the left graph. So that's perfectly fine. And now spoiler, on their turn, will play here. And now duplicator is sunk because so over here, vertex 1 and vertex 3 are connected to each other. But over here on the right-hand graph, there's no other vertex besides vertex 2 that duplicator can match to be vertex 3 that's connected to vertex 1. So let's say that duplicator plays here. Now the game is over because vertex 1 and vertex 3 are connected on the left-hand side, and they're not connected on the right-hand side. So we say that duplicator lost the game at this point, and they were forced to lose at this point in the game because there was no option, right? Playing at this other vertex, it still wouldn't be connected to vertex 1. So the game is lost at this point. It's worth noting that if you're technically playing a proper Ehrenfeucht-Fraïssé game, you are allowed to play at the same vertex. You're allowed to play at a vertex that's already been picked. But if we're going to add that condition onto the game, it makes the game harder to play, it makes the game harder to reason about, and it's never actually a strategically beneficial move for either player to make. So this particular online interactive does not allow you to do that, but there are reasons why you might want to study Ehrenfeucht-Fraïssé games where you're allowed to pick the same vertex, you're allowed to pick a vertex that has already been picked before. It is technically allowed, but this particular interactive doesn't allow it. So let's talk about strategy. So spoiler's goal is to end the game as quickly as possible. And duplicator's goal is to keep the game going for as long as possible. Duplicator wants to take advantage of the similarities between the 2 graphs. If there's a graph isomorphism, which is kind of the extreme version of the 2 graphs being similar, then duplicator can just play according to the isomorphism and run out the vertices. And if you allow picking the same vertex twice, then duplicator can play forever. On the other hand, spoiler wants to take advantage of differences between the 2 graphs. So in this case, the strategy that I kind of walked through in this example, I looked at, so spoiler wanted to take advantage of the fact that there's this vertex here that has degree 1, on the right-hand graph, and there isn't a vertex of degree 1 on the left-hand graph. And so spoiler played here, and then at that point, duplicator had to match that vertex with another vertex that didn't have degree 1, and at that point, duplicator was already sunk, right? It was only a matter of time before spoiler would be able to exploit that difference. And notice that spoiler was able to exploit that difference in 3 turns. And if we notice, this is the formula expressing that difference. This is the formula that we had that expressed that there was a vertex of degree 1. And this formula has 3 variables in it. That's not a coincidence. Those are the same number 3. And if we look in even more detail, we see that there are 2 existential quantifiers and 1 universal quantifier. And this game, if you remember, spoiler played 2 moves on the right-hand graph, followed by 1 move on the left-hand graph, right? So that 2 followed by 1 is the same as the 2 followed by 1 of the quantifiers in this formula. So it turns out that there's actually this really close relationship between Ehrenfeucht-Fraïssé games and model theory and this first order logic of graphs that I described earlier. In particular, formulas in this language, which can be used to distinguish the 2 graphs, formulas which are true of one graph but not true of the other, correspond to strategies for spoiler. If you have a formula, it takes a little bit of practice, but you can actually read off spoiler's strategy from the formula. And if you have a strategy for spoiler, you can convert it into a formula which is true of one graph and not true of the other. And in even more detail, formulas that have n variables in them, and so again, this is actually quantifier depth, but formulas that have n variables in them correspond to strategies that take spoiler n turns to implement. So suddenly we have the ability not just to reason about whether or not there is a formula that distinguishes these 2 graphs based on the question of does spoiler have a winning strategy, we can actually reason about whether how big those formulas are by looking at how long it takes spoiler in order to exploit the difference between these 2 graphs. So for instance, if we have this question, is there a way of writing that there is a vertex of degree 1 that only takes 2 variables? Well, you can prove that spoiler does not have a strategy that takes 2 turns to exploit the fact that there's a degree 1 variable, that you have to take 3 turns in order to exploit this fact, and that therefore there isn't a formula with 2 variables in it that expresses this notion, and there is a formula, well, this formula specifically, that has 3 variables in it. And we can go even one step further. We can kind of automate this process in order to prove that there is no formula at all that expresses connectivity, right? We were interested in this question, is there a formula that expresses what it means for a graph to be connected? And the answer is, well, no. Suppose that you have a formula with n variables that expresses connectivity of graphs, right? So this is a formula in first order logic of graphs that's true of all of the connected graphs and false of all of the other graphs. And suppose that that formula has n variables in it. Then spoiler has a universal strategy. Maybe they'll have better strategies for particular pairs of graphs, but spoiler has a universal strategy that only takes n turns, where n is, the number of variables, to win on any pair of graphs where one graph is connected and one graph is disconnected. And again, n might be really large, but these graphs might also be really large. So Spoiler might have, a strategy that takes 100 turns because there's a formula with 100 variables in it that expresses connectivity, and it's this really gross formula, and it's hard to prove that it even works. Um, but Spoiler would then have a universal strategy that only takes 100 turns to win on any pair of graphs where one is connected and one is disconnected, even if those graphs had like millions of vertices. And so in order to prove that this can't happen, that Spoiler can't have this universal strategy, all we need to do is produce a pair of graphs that are really big and really self-similar, where one is connected and one is disconnected, that Spoiler takes more than n turns to win on. And this is a contradiction, right? This contradicts our point that Spoiler should have a universal strategy that works. Now, admittedly, Spoiler is eventually going to win, but our claim when we said that we had a formula with n variables in it was not just that Spoiler would eventually win on any pair of graphs where one is connected and one is disconnected. Our claim was that Spoiler could win in n turns, and all we need to do then is produce a pair of graphs where Spoiler can't win in n turns. So I believe the proof is as simple as looking at the vertex graph of hypercubes, high-dimensional hypercubes. The details of this proof are kind of complicated, but ultimately, it's a place to start, right? It allows us to actually reason about this question of like, can we say this thing in this language? And we can prove that no, we can't say this thing in this particular language, which is it's absolutely astounding. The fact that we even have tools to be able to reason about these logical languages. It's worth noting that the first order theory of graphs is actually quite boring, but a lot of the tools that I've talked about here are applicable to all sorts of structures. So linear orderings, groups, rings, fields, any sort of structure that you might want to talk about, you can reason about the first order logic of that structure using some sort of modified version of the Ehrenfeucht-Fraïssé game. And in fact, if you go online, you can also play this game on infinite linear orderings. So here we have, oops, let's try that again. Those are finite linear orderings. So here we have some infinite linear orderings, and we can play the Ehrenfeucht-Fraïssé game on those as well. There's no AI for this because it's really hard to build an AI for infinite games. It's possible though, which is kind of neat, but it is quite difficult. So the first order logic for graphs it's not very expressive, and it turns out there are actually some really cool theorems about how unexpressive the first order logic of graphs is. If you really want to reason about graphs, you really want to use second order logic. So second order logic adds in a new type of variable that allows you to talk about not just vertices, but also sets of vertices. And we can talk about, a vertex being in a set of vertices, and we can talk about for any set of vertices, and there exists a set of vertices. And in that language, you can talk about things like graph coloring. You can talk about things like connectivity. You can talk about most of the properties that you'd want to be able to talk about when it comes to graphs. But of course, this is kind of a double-edged sword because suddenly everything becomes NP complete as well for certain formulas. So it's a very expressive language, but it's also very hard to analyze because if it were easy to analyze, then it would be easy to prove that P equals NP. And we know that it's not. But it's still very useful. We can still play Ehrenfeucht-Fraïssé games on second order logics. The point of the game is to really give you an intuition And Ehrenfeucht-Fraïssé games really don't do a good job of giving you intuition about second-order logics. But there are some tools. There's something called Courcell's theorem that allows you to analyze problems involving second-order logic and graphs using finite state automata of all things. That's kind of the state of the art in terms of reasoning about graphs and their second-order properties. And of course, as I've mentioned, all of this, the Ehrenfeucht-Fraïssé games, model theory, all of this stuff works not just for graphs, but all sorts of other structures as well. So it's a really interesting field of logic, and I encourage you to check it out.